Do you dream of electronic systems design? Okay, maybe it's just me. But when I dream of electronic systems design, I imagine myself coming up with the best idea the planet has ever seen. Throwing down a few lines of code and maybe a swirl of a magic wand, and then bam! The design is complete and ready to roll out across the globe. And yes, I am aware this is just a dream, and we are years, decades maybe, away from this becoming a reality. But what does electronic systems design look like in the near future? I'm glad you asked, because that's exactly what we're talking about today. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, David Wiens from Siemens and I explore the role that AI, cloud connectivity, and security will play for the future of electronic systems design, and how Siemens is furthering innovation in this area with its integrated suite of design tools. And before we get started, don't forget to click that link. There you can find even more information about this topic from Siemens. Hi, Dave. Thank you so much for joining me.
Hey, Amelia, good to talk to you again.
Excellent. Okay, so we're talking about the next generation of electronic systems design. But before we talk about the solutions in this arena, Dave, what do you see are the biggest goals and challenges here?
Well, first of all, as far as electronic systems design, I mean, this is board design, but it's more than that. It's how the packages engage and interact with the board. It's multi-board design. It's cabling, it's software, it's everything that's necessary to get electronics integrated into a system. Now, as far as the challenges here, well, first off, let's look at some goals. We've got folks that have to keep pace. Electronics doesn't sit still. There are constant innovations that teams have to learn about and keep up with. They've got to differentiate their products. So they've got to leverage the latest technologies. When they create new products, they've got to get them to market as fast as possible. So they're looking at challenges like resources. Do I have the right people? Do I have enough people? Do I have enough compute power? They've got obviously the competitive pressure and then the market volatility. We saw plenty of that in COVID, but it continues today.
Absolutely. Now, let's talk more about that first challenge you mentioned, resource constraints. What would you classify as a resource constraint?
Resources fit into a couple of categories. One is the people, and two is the compute power. And both are necessary to be able to address today's complex design challenges. On the human side, engineering teams, we hear consistently, are faced with resource limitations. We have a demographic shift in place. It looks like an inverse bell curve where you've got a bunch of guys on one side, they're expert, but they're retiring off. And on the other side, you've got the new engineers entering the workforce. They're inexperienced. And in the middle, you've got a kind of a vacuum. It's not obviously empty. There are a few people there, but it's a distinct bell curve in that context. And the problem with the new engineers is that there aren't enough of them. Some estimates say that up to a third of positions will go unfulfilled. So engineering teams are constantly struggling to get people to enter the workforce and support the latest design challenges.
So, we're also looking at the acceleration of innovation here as well, right?
Yeah, absolutely. Electronics is in everything, first of all. So that's more design starts than ever before. Lots of new areas to attack. But the cycles of products, well, there's two kinds of cycles. There's a life cycle of the device, meaning, how long is it expected to last? And then there's also the release cycle. And both of them are getting shorter and shorter. Release cycles are getting down to months in some cases. We see that fairly frequently, actually. And then, the life cycle of a product is diminishing, as everyone with a cell phone knows.
Dave, we also need to consider changes in the market too, like you mentioned earlier.
Yeah, and this is something that there's a few things that are normal and a few that aren't. One of the normal things is just the increasing electronics, right? It's everywhere. That's more predictable than unpredictable. The unpredictable stuff comes in the form of supply chain volatility, for one. Can I get the components I need when I need them? Can I get the materials for the board? Can I get fab shops to support me when I need them to? All of that's volatility that engineering teams have to develop multiple sources for. to be able to effectively get a design done on time. And then there are the trade wars, the geopolitical issues that continue to cause problems for every engineering team, regardless of where they are. But you're seeing things like onshoring, for instance, where a lot of designs were built in limited numbers of countries. And because of either geopolitical issues or supply chain issues, you've got some onshoring going on. And that changes cost and time. So there are lots of variables to consider. The last one, the last kind of unpredictability is those advancing technologies. And I talked a bit about those before, but this particularly comes in the form of IC packaging, the new advances there. Another one, though, is additive manufacturing. It's entering the electronic space, and that brings an opportunity, but also a challenge in terms of adapting to that technology.
That makes sense. Now, Dave, can we step back a bit and talk about the evolution of electronic systems design a bit?
Yeah. So, Amelia, for those of us who've been around for a while, we've seen a lot of these phases develop, but I wasn't around all the way back when people were doing tape and mylar on cutting boards. But the first generation of electronics software came in with basic, CAD design. You were replacing the very manual, very physical element with digitization. That was very immature as an approach. There wasn't much intelligence. There definitely wasn't any automation. Then the next generation of tools started coming in where people tried to glue together environments. And so flow integration became a critical thing. It wasn't just having unique domains, but they had to work together. And then we entered an era where automation became more important and multidiscipline design, being able to work across multiple fabrics, came into play. And now we're, at really this cusp of what we'd classify as next generation, where tools need to leverage advanced technologies like AI, like cloud capabilities to really create these intuitive environments that everybody can use and use them as efficiently as possible. So really, the goal is overcome those resource constraints, develop resilience and adaptability, and leverage, initiatives. And we hear this from companies, what's your digital transformation plan? What's your AI implementation plan? And so trying to, adopt those technologies as quickly as possible, both on our side and on the customer side.
So, where is electronic systems design headed from here?
What you can see, our view of electronic system design and what we classify as next generation electronic system design is evidenced on the left. And starting in the center, first off, let me note that you see this brand called Siemens Accelerator. That's a brand that is an umbrella brand to all Siemens software products. It indicates that we are a part of a larger enterprise and we integrate those tools closely as a result. And I'll talk about some of that stuff later. We use that technology to address the critical challenges, the ones I talked about, the resource issues, the time to market, differentiation, security. The way we do that is through a technology that is, first off, adaptive. It's adaptive to the needs of both new and experienced users and how they want to work in a personalized environment. It's efficient as a result of that. And really, efficiency is something that's tough to imagine when you think about, leveraging the most complex products in the world to design the most complex electronics. And so bringing adaptive and efficient together is critical. And then enabling collaboration with a broader ecosystem. It's not just about yelling over the wall to the guy next to you. It's about collaborating with an ecosystem of engineers who may not even be in the same company. You've got partners, you've got suppliers, and they all need to work together as efficiently as possible. And then because you've got data flying around all over the place, you got to figure out ways to manage that data to minimize any risks from cybersecurity attacks that might come along. So to continue on with that, if you look to the last ring, you can see how we're trying to create this technology and really what it can bring to users. And so the first pillar that we talk about is intuitive. If you've created a product that's adaptive and efficient, hopefully it's intuitive. And that's what we have validated with customers already to determine how efficiently they think they can work with this new environment. But an intuitive tool really works to boost the productivity, leveraging a modern user experience. This means taking advantage of modern UX principles, things that you might see on your desktop already, so that the design tools operate fluidly with other tools on your desktop. The next is AI infused, and this is partly related to the intuitive side in terms of things like automation, trying to make tools easier to use, but also accelerating design automation. The third area is cloud connected, and I talked, briefly about that in the context of the ecosystem. But how do you enable teams to collaborate seamlessly across that broader ecosystem? And then the system needs to be integrated. And this is an area we've talked about. I referenced earlier the evolution of design, and integration was something that came up earlier, but it's a continuous challenge and it's a continuous opportunity as well for organizations to create that digital transformation across their entire design spectrum. And so we can work with them to create those digital threads. And then the last one, again, is security, trying to ensure that data, wherever it lives, whether it's in the cloud or whether it's on the desktop, that critical IP is protected.
So, Dave, can you address that intuitive pillar you mentioned? What do you mean by that?
So, Amelia, first off, intuitive is in the eye of the beholder, of course. What it means is, again, making a tool that inherently is complex to address complex design challenges, making it simple, making it more adaptable and more adoptable by new users so that the learning curve is greatly reduced. That's something we've heard for a long time. You can become an expert in any tool. How many years does it take? We want a tool that can be easily adopted. We went through an extensive beta cycle. It was over a year long, 5 different cycles of product revs, over 250 participants in it. And these are, so to speak, tough customers, right? These were customers, users of the tool, but people who had grown used to the environment as well as potential new users. And you see comments like, was able to figure things out before reading instructions. Tell me the last time you saw that related to an EDA tool. And another one, just looking at it makes you want to use it tool some more. It's not just about new users, it's about improving the efficiency of expert users as well. And one of the things we've done, one of the ways we've brought this technology forward is by infusing the common user interface across our portfolio. So products that engineers are used to, like Expedition or Hyperlinks, have this common UX across the flow. So you can pick up one tool one day and another tool the next, and you're used to working in it. Something like you might expect in say, Microsoft Office. This, again, is a new concept in the world of EDA that you can imagine. You could go from a design tool to a simulation tool and expect them both to work the same. So it took a lot of time. We've been working on this release for over 4 years.
Fantastic. Now, let's also talk about AI infusion here. Where do you see that playing a role in electronic system design?
For starters, Amelia, we've infused AI in that user experience that I talked about just now. You can see an image of that on the right here. We've put what's called predictive commands into the product. What this enables teams to do is, first off, we deliver it with a seed model. And this is based on our experts using the product saying, well, okay, we think once you've done this command, you're going to likely do this command. So for instance, you place a part and then you rotate it, or you push it, or you fan it out. And so all of that is seeded into the model. And then once a user starts working with the tool, it adapts to them. It's using a machine learning algorithm, and it adapts to their use model. And so that whatever they do next is likely to appear right in front of them. So they don't have to go searching around any menus, searching for anything. It's sitting there right in front of them. Another use model is that they take the seed model that we deliver and they flush it and give the tool to their own expert user with their own process and train the model that way, and then pass that model around to all the junior engineers to learn from them. So there's a few different ways where AI can be leveraged just with the user experience. We talk about AI infused. It's more than the UX. We've got AI in a number of areas. We've got large language models that have been used to enable in-product chat to get people answers to questions they might have right there in the product. We've got a language-based search, natural language query of data sheets. So you can find things as quick as possible. Again, you're not searching around a data sheet looking for critical information. We've also got it within the supply frame engine. Part of the thing that we've developed is the ability to do better part research. And that part research engine is powered by supply frame, and supply frame uses AI to analyze what we could call digital exhaust. the results of all the search that people have done for different parts. And it can aggregate all that information and give you ideas of what parts are popular, what parts are going to soon be unavailable because everybody else wants them. So AI is leveraged there. And then the last area that I could talk about here is leveraging predictive AI within our analysis engines. And a quick example there is doing design space exploration. You could imagine looking at just a 3D model of a differential via going through a few layers. It's got shielding vias around it. It's got and then you got to figure out, okay, what's the exact dimensions I want to use for that to optimize the performance. It's a very simple problem, but that particular example can have up to 8 variables, and each of those variables has a range of values that works out for it. Just playing with that one example, I calculated up to 24 million permutations. So if you swept every single variable, you'd get 24 million permutations. By the way, if you take an average run, about 10 minutes, that's going to be measured in generations, right? So it's over 200 years. Obviously, nobody's going to mess with that. What do? So they usually just simulate a few different options. Maybe they run a sweep on one parameter and they call it good. They say, I don't know what the optimal solution is. We're going to call it good. Well, we've leveraged AI to enable with a limited budget. In this case, we gave it a budget of 100 different options, and it can go out there and find the best option. If we gave it that budget of 100, it could go overnight and come back with a result. That's much better, obviously, than multiple lifetimes of people. So that's just one example, I guess another example, I've given you a few, of where AI can be added to the equation. I should note, being part of this larger Siemens accelerator portfolio and ecosystem, we have the ability to leverage technology from multiple groups. The AI that we're leveraging with predictive commands came from another group. You might know them as NX, the mechanical engineering team. And the design space exploration came from SimCenter. So we have the ability, within this company to leverage the technology across divisions to solve a common goal. And that's just, another power of the Siemens ecosystem.
So, Dave, cloud connectivity is also a crucial design concern to keep in mind here as well, right?
Yeah, cloud connected comes into play, as I mentioned earlier, with a larger ecosystem. Leveraging cloud technology comes into play there. I should note the majority of our tools are still desktop based and probably will be for quite some time. But there are opportunities to leverage cloud. And we've done that in particular with that larger ecosystem at the front end, enabling engineers to do better part research and part selection, being able to look at trade-offs and have multiple sources of parts. All of that is based on cloud technology. And then collaborating with partners outside of the design engineering team, again, leveraging cloud technology. And the final area is collaboration with manufacturing, enabling a seamless digital thread of constraints coming from manufacturing. What rules would they recommend that you use to achieve optimal yield from their manufacturing process? We can test the design, run those verifications on the design, and then pass the data back seamlessly across that platform to manufacturing.
So, integration is more important than ever before, right, David?
Yeah, it's as I noted before, it's something that we've been talking about. If EDA vendors haven't been integrating, customers have been doing their own integrations to try to enable that digital transformation, that digital thread across design tools. And those are fun marketing buzzwords, but the reality is if you don't integrate tools together, what you have to do is do some level of rework. And the most common one is between design and simulation tools, where you can pass a basic model across at best, and then you get in the simulation world and you got to recreate half of it, simulate it, hope you got it close to right, and then maybe, communicate by a sneaker net back, that this is the actual structure that's going to work for you. That's a lot of pain. That's a lot of, that rework takes time. It introduces errors. And so it's a very real problem that engineering teams face. I should note, though, that it's not just between design authoring tools, PCB design authoring tools, and simulation. It's across multiple domains. It's between ECAD and MCAD. It's between ECAD and electrical design. It's between the design tools and the PLM tools. If you look to earlier in the design process, it's between the architectural and requirements definition into the design space. And then on the manufacturing side, I gave you that cloud-based example, but trying to integrate as best possible between design and manufacturing. So it's really an integration across the entire flow from initial concept through manufacture that's critical.
And of course, we need to talk about security as well, right?
Security is critical in the context both of where data rests as well as data that's in transit from one location to the next. It's a concern for desktop environments as well as cloud-based environments. So there are a lot of critical things that our customers have had to deal with to support that. But more recently, there are additional constraints on export controls, on data security, particularly for mil-aero designs, but as well for other things just like consumer designs. So what we have enabled is the ability to define who can have access to which project where. It's not just enabling an engineer to be able to access a project. You got to be able to say where you're at, and it will test you for that so that you can't necessarily just open the design anywhere you want and potentially introduce a cybersecurity threat. So again, who can access it, which project, and where.
All right. So to wrap things up, Dave, what would you like my audience to take away from today's Chalk Talk?
I brought up this idea of a next generation. This to us is a significant new release of our portfolio. We've been known for a long time for addressing really complex design problems. We've also been known for creating really complex design tools. And so we've addressed that with this intuitive user experience, one that we believe will enable teams both for their new upcoming engineers as well as for their experienced engineers to get designs done more efficiently. We've added AI to the flow, both to accelerate productivity, kind of coupled with that intuitive component, also to enable design space exploration to optimize the end product. We've added cloud-connected capabilities to enable teams to collaborate more efficiently across the ecosystem. And then we've done additional work on that integration, really enabling teams from initial requirements through manufacture to be able to work with and establish a digital thread, minimizing any rework that might come along. And then last, again, tying it together with security, enabling teams to protect their critical IP and comply with regulations that are emerging, for instance, the export compliance. So Amelia, that's pretty much it in a nutshell. I know there's a lot of stuff here. I'd recommend, first off, we'll put a link out there for the intuitive stuff. I think that's really cool to see in video. So I'd recommend that you hit that link. It's pretty easy to find the videos out there that show off the new UX amongst other features. So please take a look.
Fantastic. Well, Dave, I think that's all I have time for today. Thank you so much for joining me.
Thanks, Amelia, for hosting this event, and goodbye.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Siemens. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.